Okay, now we're gonna do something different. We're gonna plug two batteries in series, so we have more voltage at the end of our transistor. So the light is a little bit stronger than before, and another thing is we can have bigger distance than we had before. Okay, I was trying to measure the voltage in the switch, and I put the ground here. Then I was trying to connect my positive pole, and I noticed something. Without connecting, I have a voltage, and I was like, I want to measure that voltage, and let's see what happens when I try to put it closer and closer. This is the diagram of our Tesla coil. We use a transistor of 2222A, and we use a battery of 9 volts, a resistance of 22K, and our first coil with wire is wired with 300 turns, and the second coil is with 2 turns. To understand how it works, the Tesla coil, first we need to know the transformer principles. We need to remember that the Tesla coil is just another transform, but with air core. If we want to know the voltage on the secondary coil, we just need to multiply the voltage on the primary with the number of turns of the secondary coil divided by the number of turns of the primary coil. And with this equation, we can have the voltage in our second coil. Something similar happens with the intensity. If we want the intensity of the second coil, we need to multiply the first intensity, the intensity of the first coil with the number of turns of the first coil divided by the number of turns of the second coil. Due to the fact that the Tesla coil doesn't have a metal core, the intensity efficiency goes down by 80%. So we have an efficiency of 20%. The scatter flow of the primary coil exceeds the secondary coil, and it makes the flux, the magnetic flux, in both of the coils.
This is the class of Dr. Roberto, and he is going to explain a problem according Stokes theorem.
Okay, Andres, please read the exercise, please.
Okay, calculate the current flowing through the surface delimited by 0 to 2 pi in phi r minus equals to 3.5 meters, 0 to pi divided by 7 in theta if the magnetic field intensity is given. h is equal to 6.4 e elevated minus 5 r second of theta in the 5 direction.
Okay. According to Stokes' theorem, the current equals to the double integral, that is the surface, and this equals to the double integral of the partial derivative cross product with the vector h. From the result of this, we have to do the dot product with ds. This is the left side of this equation. Okay? The ds equals to square r sine of theta d phi in the direction of a.
And how can we know that? How can we find ds?
Oh, okay. Let's find out. This surface is a section of an sphere. This is a little surface, and this is a curve. If we see this curve, this surface, and in 2 dimensions, we get this. And how can we know the area in this surface?
Cutting the surface with a lot of circles.
Yeah.
Okay.
If we have little pieces of this, we have to multiply per every one and we get the surface. According to the accordion, this side equals to r times sine of theta
Okay.
d phi. And if we want to know the area, we have to multiply this times this. This side equals to r times d phi.
Okay.
And the result is that.
Okay. And why you have r direction? What does it mean?
R direction. Oh, the meaning of this is that the vector is in direction of r. This is the radio of the sphere.
Okay.
This
So
comes.
it's like going like this, out of the surface, like that.
Yeah, exactly.
Okay.
Okay. And the third step is find the partial derivative and cross product with h. We have to do it.
One
Yeah.
question.
Tell me.
If I'm gonna do the dot product, and this one just have component on r,
Yeah.
could just use this one and not do this whole thing?
Yeah, exactly. This is due to the direction of the vector. We
Okay.
only have to use r, and the rest of the expression is gonna be cancelled.
Okay.
And if this is gonna be cancelled, we get this is cancelled. We get this and this,
No. Okay.
but this is gonna be cancelled too.
Okay.
And this is the only term that is gonna survive, and we have to do the operation, for example, the multiplication, but the first one is do the partial derivative of the vector respect to theta, and after that we do the multiplication. This is the result. We can notice that the letter r is going to be cancelled, and at the end we have to solve the double integral. The limits for theta are from 0 to pi over 7, and the limits for phi are from 0 to 2 pi. And if we solve the double integral, we get the result.
Perfect. Okay.
And if we want to know that this is correct, we can prove that this is true using the right side of Stokes' theorem.
Okay.
Okay, Andres. Ahora. Okay, Andres. Now try to solve the right side of this equation to prove that this is true. And it's easier than the left side.
Okay.
Come on.
Alright. Well,
You can do it.
I suppose we're gonna do the dot product with DL. To find DL is easier because we have this surface, this circle. It just has one line. Perfect. We're gonna use r sine of theta d5. Okay. This is gonna be in 5 direction because every time we have a line integral, we use the same direction of the differential. By doing that, we can notice that this one and this one will cancel. Well, we'll make a dot product and we'll survive all the terms. So I just have d5. I can take out this constant and it's 6.4, the line integral, but it goes on d5. So I'm gonna use this part from 0 to 2 pi.
Yeah, exactly. The limits of 4, 5.
Okay.
Yeah.
And now a minus 5 r times r squared. Second is the same as 1 over cosine of theta,
Yeah.
multiplying by sine is equal to tangent
Yeah, exactly.
of the 5. Okay. This is gonna be tangent of theta, and this is a constant in this case because we are integrating in d5 with respect to,
5.
and this is gonna be a constant too.
Yeah, exactly.
Okay. Can I erase this part?
Yeah.
Okay. Well, I forgot this part. Is multiplying by 10 to the minus 3 in the power.
Yeah, exactly.
Okay, I can do like this. R multiplying, what is R? R is 3.5 meters, but in this case I need that. This is going to be tangent, and tangent of what? Of
Theta.
okay, of this, right?
Yeah.
Okay. Don't. Okay, multiplying by the result of this integral. Am I right?
Yeah.
Okay. If I put all that in my calculator, let me see what I get. 6.4 times 10 to the minus 3 times 3.5 square times tangent of
Something is missing. Sorry.
okay,
Continue.
pi over 7 and okay, I'm gonna do like all these and then the integral.
Yeah.
With this I get 0.3777 oh no 5 times here's a 0 sorry teacher,
Don't worry.
and I'm gonna do this integral is a over x, in this case, from 0 to 2 pi. The calculator needs to be in radians.
Yeah.
Why? Because we're using trigonometric or what?
And this is due if we use this expression, for example, pi 7, we need to use a calculator in radians. And if we use degrees, for example, 30 degrees, we have to use a calculator in decimals.
Ah, okay. Can I read?
Yeah.
Okay. So it's in radians. Give me 0.99813, and we multiply this times 0.0037755. Oh, it's the same.
Yeah, this is theorem.
Amazing. By both sides we get the same thing. Amazing.
Okay, Andres, that's it. You have got a A++.
Thanks, teacher. This is gonna be our distance. In the cell phone we have the magnetometer. And now we're gonna put it closer to my clock, my alarm. So it had like 3,000, I think so. 3,000. 300, 300,000. Perfect. Now we're gonna measure another thing. Let's try to measure this thing. Okay. It's on, so it must be a little bit higher. Oh, look at that. Acércalo, acércalo.
Oh,
Ponlo de lado.
¿de eso?
So you can notice this change. It's a milli change. Okay, pause. The next thing we're gonna measure is the fan without plugging it. Okay, we can see. Okay, now I'm gonna turn on the fan. Okay, let's see. Pause. This is our next device. Is a Wi-Fi of the house. Let's see. We can see you have almost nothing. Almost nothing. I think aquí debe estar la antena. Well, there was a Wi-Fi modem. Now we're gonna try to measure the funnel. Okay, this is really interesting. Acércate. Oh, no, acércate más. Para que se le quite la... Acércate. I think this change might be because of the... ¿Cómo se dice usted?
¿Aquí?
Acércate, acércate. Yeah. We were trying to measure the density flux, the magnetic flux, with our Tesla thing, and this is what happened. I'm not touching nothing. But, I don't know why, but that happens. Yeah.
Ya.
Ponla en contra de lo negro. Ponla en contra de lo negro. O sea, que se vea lo negro ya.
Ahora míralo.
Now.
Ahora apágalo y míralo.
Perfecto. Ya. Si nada tiene eso. ¿Ok? Ya. Ahora yo le voy a pegar esto aquí. Y le voy a tratar de... Ah, hay que prenderlo, puede prenderlo. Dale otra vez. ¿Viste el pico que hizo?
Sí.
No está muy chido este. Bueno, pero ya. Ya. ¿Viste eso?
Pégalo más.
Ya. ¿Listo? Ah, pásame. Espérate. Dobla conmigo. Dóblate conmigo porque se... Pégate, pégate, para que se vea. Oh, wow. Wow. Acércate, acércate, acércate mucho.
Más. Ya.
¿Qué debe haber ahí? Oh, wow. Cerca. Oh, cielos.
Oh, cielo santo.
Entonces aquí. Algo hay. Ya. Pues. Mira, hay una variación ahí. ¿La ves?
Sí.
Acércate, vamos a ponerla.